Hi, so this is the lab section now. So first of all, if you don't have these particular libraries, you should try and install them: the tidyverse, the ggplot2, the ggpopr, and also the coin package. So you should just try and install these particular packages. I'm just going to run them. If you don't have them installed, so you should install them. So first of all, now I'm going to be creating a sample data set. This is a BP data. It's actually a simulated data. We have patient ID, we have the before, and we also have the after. So I'm just going to run this, and when I run this, I'm going to view it head BP data. So you can see it. This is the head of the BP data. We have the patient ID. This is before of their BP, and this is after they're already taking the particular medication. So we want to calculate the differences now between the before and the after. Now we're calculating the differences, so we just run it now. We check for the head BP data. So you can see it. If you check the head of the BP data, so you can see this is the difference between the before and the after. So we can check normality of this difference by first of all running an histogram. So this is the histogram. So you can see the histogram of the BP data. So you can see that it's not normally distributed. We can also look at the QQ plot. So this is a QQ plot. I told you that most of the lines have to fall on the line. You can see a lot of them are outside. You can also look at the box plots. This is the box plot. So the box plot, I don't know, it's supposed to show. So this is actually the box plot. So we have already viewed our data, and finally you can do a test for normalities in the Shapiro week. I can see it is actually 0.3318. So, and the Shapiro week, if it is less than greater than 0.05, it means that what the data is likely normal. So we should use a parametric test. But if it is less than 0.05, we will not use a parametric test. So we can still say the data is somehow normally, because if you look at the line we have, a lot of them closely fall on the line, and even the histogram is closely normally distributed, except for this particular blank space that is in this place. So first of all, we are starting with the Leucoxin rank test. So the Leucoxin rank test is the non-parametric alternative to the paired sample t test. So we're going to be using our BP data. I already check our BP data, and let's just have a descriptive statistics of it. So this is a descriptive statistics of the before and the after. So we're going to calculate the median of the before. What do we have? 141.7998, and the interquartile range of the before is 15.63421. So these are the measurements of location and measurement of spread for a data that is not normally distributed. Now we are assuming our BP data is not normally distributed. That is why we are using the Wilcoxon signed rank test. So let's check the median of the after, which is 127.9, and the BP data after the IQR interquartile range is 20.59. So I'm going to perform the Wilcoxon signed rank test on this. So I'm just going to run this. So when I run this, we print the Wilcoxon results. We'll print the result of the Wilcoxon test. So you can see that our p-value is 0.009436. So we reject the null hypothesis that what the two samples have the same median. So this is what we have as our results. So for a one-sided test also, we want to check now. For a one-sided test, I told you this one is a two-tailed test. If we are equal or not equal. For one sided, we're trying to say maybe that of after is less than that of before. So let's see if that is true. And we'll make sure you give paired as true in the Wilcoxon test, and your alternative should be less, since we're using a one-sided test instead of two-sided. And you should get your confidence interval. So when I run this now, you can see our p-value is significant, which means that what the value of the median after the take the dosage, you significantly reduce the BP compared to before the BP was taken. You can also try to visualize it now. So just going to visualize the peer data now. So this, we are trying to create the data into a long data. We are trying to create this data, form it into a long data now. Difference, I can see the time point. So I've made those columns now to become levels under time point variable. So I'm now going to run this GG paired. So you can see it now, already visualizing the time point, and you can see that what you can see before, you can see after, that is actually significantly different. So that of after is significantly lower compared to that of before. You can see the median, because this is in box plots. You can see it is currently higher for that of before compared to that of after. So even from the box plot, you can actually notice significant difference. So what are the effect size now? So the effect size now, this is the formula for it. It tells us how big the difference is now. So you have to make sure you install this library rstatic, and we are going to run this now. So when you run this now, you can see the effect size is 0.568. So if the effect size is between 0.1 to 0.29, it means it has a small effect, the difference, but it is between 0.3 to 0.49, there is a medium effect, and if it's greater or equals to 0.5, it means a large effect. So you can see now that we have something effect size that is greater than 0.5, 0.568, signifying that we actually have a large effect. So now this is for the Mann-Whitney U test now. So the Mann-Whitney U test now, I told you that we use the Mann-Whitney U test for an independent, is the non-parametric alternative to the independent sample t-test. So I'm going to create a sample data now, as you can see in this place now. Just check the head of this particular data, recovery data. And you can see you have drug A, also have drug B. So you take the tail of the recovery data. We have drug B. You can see drug B below. So descriptive statistics now by group. So I'm just going to run this, and you can see the number, you see the median, you see the IQR, you see the minimum. So these are the various parametric measurement of location and scale, location and spread. So you can also visualize the distributions using the ggplot2 function. So you can see the distribution. You can see that what the particular median of drug B is actually higher recovery time compared to that of drug A. You can also try to check for the normality by group. You can see the result of Shapiro-Wilk test indicates what non-normality. So now let's perform the Mann-Whitney U test using Wilcox.test function. We say two-sided goes to true recovery. That you also use the same function to perform a Mann-Whitney U test. Then you run it. After that, it's also the Wilcoxian is also known as the Wilcoxian rank sum test too, also the Mann-Whitney U test. So now you can see our p-value 0.963, which means what there are actually no significant difference between the two of them. So we have a p-value of 0.9693. So we cannot reject the null hypothesis. So the median are almost what the same. So this is what this particular analysis is trying to tell us. So for one-sided tests, if the recovery is of A drug A is less than drug B, we just change the alternative to less. We also run these two also. What do we have? We have 0.487. So it is also what's not significant. So recovery time of drug A is not less than that of drug B. Because even from two-sided, it shows us that what they are both having equal median. What is the effect size? Let's check for the effect size. So you can see the effect size is very small. So which means that what, because this should not be surprising since the result was not actually what significant. You can also try to just plot a violin plot to visualize it. So even though from the diagram you could see that as if the medians are far from each other, then the medians are just far from each other, but they are not actually significantly different. So the Kruskal-Wallis now is alternative for the one-way ANOVA, or you have three or more groups. So this is sample data we just created. Pain data, pain score. Okay, sorry, pain data. It should be pain data. So this is the placebo, and you can see tail, pain data. This is the dose, pain score. So placebo. So you can see it now. We have the head, we have the tail. So make a dose an ordered factor. We want to try and make our dose now an ordered factor, because we're having 4 levels of dose, and we just get the descriptive statistics. You can see our various non-parametric measurements of descriptive statistics, the median and the interquartile range and important things. So then you can visualize it using the ggplot. Because this, so even though now we have various possibility here, is either their medians are actually significantly different or they are the same. So because you can see them, that of the dose level of those under high, so the pain scores of those under high dose level, can you see is low compared to those under placebo. So let's perform the Kruskal-Wallis to see what our result is. So if you check our Kruskal-Wallis, you can see that our p-value is actually very small, which means there's a significant difference between all the 4 dose levels. And let's look at the effect size to see what our effect size. So 0.564 means we have a very large effect size. So we use the post hoc comparison to check which of these particular dose levels is significantly different from the others. So I'm going to be using the Dunn test with Bonferroni correction to look at which of these particular dose levels is significantly different. So I'm supposed to run it. When I run it now, it's going to give me the dose level of each particular group. So, okay, I think you should just view it again. Let me see. Done results. So we have, can you see, for this is group 1, this is placebo and low. You can see that it has a small p, so that means that's significantly different. Placebo and medium, also significantly different. Placebo and high, also significantly different. Low and medium, significantly different. So almost all of them are significantly different, since you can see they all have a very low p value. So that is it for the post hoc test. So for the sperma rank correlation, now I'm just going to use another sample data of study hours and exam rank. I'm going to use study hours and exam rank, then student ID. Then I'm going to add some monotonic linear relationship between it. So let's just view it, the study data. These are study data, study hours, exam rank. Add some monotonic non-linear relationship. You can see it. Then view the study data. Then descriptive statistics, you can get it, or these are descriptive statistics. They can visualize the relationship between them and C. You can see this a little bit curved, not straight, though almost trying to be straight, is a little bit curved. Then you can now perform the Spearman correlation using the core.test function. The only thing you are changing is just changing the method to Spearman instead of Pearson that we used earlier on. So when I just try to run this now, I'm going to be getting my p-value. So what did I get as the value of my rho? So you can see my rho is minus 0.987. So you can see it's almost close to 1. So this is a negative relationship, which means as study hours increases, then the rank also decreases. This is what we are getting. So let's compare that with the Pearson. What do we have with the Pearson? Also of minus 0.95. So the increase in study hours, then the rank decreases. Yeah, if you notice, the lowest is the best student, which is 1. If you know the rank, this is how it goes: first position, second position. So when the student spends 30 hours, he's likely to get that particular lower value, so closer to 1. So that's what it's trying to mean, which is actually true in real life. So that is what it means by this particular result we have get. You can see similar to both the Pearson and the Spearman are almost similar. You can see their values. This is correlation coefficient, while the Spearman uses rho. So this is a strong negative relationship. So let's use the correlation matrix to also visualize it using the core plot library. So use the core plot library. You can see the study hours. This is a comparison between the Pearson and the Spearman. You can see it. Then you can see our correlation matrix. So this is the study hours, exam rank, and study hours is around minus 0.99. So this is just a simple explanation of how you can use the non-parametric alternative for correlation analysis, which is the Spearman rank correlation coefficient.